Hey there, welcome to Solve My Math Homework. We're the YouTube channel that solves only the problems our subscribers submit. So today we're going to make sense of altitude on the hypotenuse theorem. So we're given this problem. It's a triangle, it's got an altitude drawn in, and we're going to investigate three different relationships within this. So it tells us that angle JOM is 90 degrees. So JOM is right here. It's within a triangle. Anytime we have a 90-degree angle within a triangle, we have a right triangle. That's pretty easy. Then it gives us a little more information. It tells us that OK is an altitude. All right, so this segment OK is an altitude. What makes the relationships unique is that the altitude is drawn to JM, which happens to be the hypotenuse. And that's what we're going to investigate today. All right, so before we get into this, we really have to look at this altitude on the hypotenuse theorem. So the problem tells us that this piece here, JK, is 12 units and KM is 5. And it wants to know the length of that altitude. All right, but we can't do any of that until we look at this theorem. So let's get started. All right, so I have drawn, not well, but I have drawn this ABC, this right triangle that is divided with an altitude drawn to the hypotenuse, so that we could look at some of these relationships. So let's take the first thing that we know about right triangles. We know that right triangles have measures of their angles that equal 180 degrees. Okay, so if we look at the larger triangle, the ABC triangle, I know that angle A plus angle B plus angle C equals 180. I also know that angle C is equal to 90 degrees. All right, so let's go ahead and make a relationship with that. Let's go ahead and say let angle A be X, and let's let this one be Y. So then what do I know now? Based on what I just said, I know that X plus Y plus 90 equals 180, based on that sum of the angles being 180 relationship we talked about. All right, so let's look at the individual triangles again then, okay? So if I look at the medium triangle here, I know Y plus 90 plus something equals 180. And if I look at the small triangle, X plus 90 plus something equals 180. Given the relationship we just worked on, I can say that Y plus 90 plus X equals 180. And in the same instance, X plus 90 plus Y equals 180. So that's a little bit messy, sorry about that. But that tells me that yes, I have three similar triangles, and they are similar by the angle-angle similarity theorem that tells us if you have two congruent angles within triangles, then you have three. All right, so the important thing here is really to make sure we're looking at the right angles and the right triangles. When we say similar triangles, we really have to be specific. So I'm going to break these three out. They're kind of messy anyway. I'm going to take the small one, the medium one, and the large one, and I'm going to orient them the same way. So let's do that so we don't have to look at this anymore. I want all of my right angles facing left. So if I look at my smallest triangle, that's going to look like this. Here's my right angle, bottom left. And that's going to be, right here, that's going to be D, right? The smallest angle goes up to C, and it goes down to A, all right? Now looking at labeling my angles, this C up here is Y, and this A down here is X, and so I should put those in because we took the time to do them. And to see three similar triangles, I want to see three corresponding congruent angles. So up here I have Y, and down here I have X, and that's my small triangle. Now let's take out the medium triangle. Okay, so my medium triangle is going to be this guy right here. So the right angle's down here, I want it bottom left, so I'm going to have to kind of flip this up, right, up this way, and then reflect it. All right, so when we do that, it looks something like this. We've got this down here. We've got our right angle down there. That is D. And then it goes up to B, right? It comes up to this guy B. And then when it kicks out to C. And so once again, let's go ahead and label those angles that we worked so hard to prove. Okay, so C is going to be our X, right? Because it's right there, it's what we kicked out to, making B Y. All right, and we have one more triangle. We have the large triangle. We want to look at that one. That one's usually the easiest to see, but let's go ahead and look at it. Here's my right angle. I want it bottom left, so it's going to be a base of CA kind of coming up to B. So let's do that one, and let's get a new color. All right, so let's say here's our big one. All right. There's my right angle, bottom left like the rest. This guy is going to be C. goes up to B, and kicks out to A. Labeling my angles, okay, just like in the first one here, angle A is X and B is Y. And now I have 3 similar triangles because I have 3 triangles with corresponding congruent angles. Now it is really important to kind of get it down where those vertices go. We can't just say CDA, BCD, ABC. We have to be very specific. So when I tell my students that they're going to name their similar triangles, I say make sure you go in angle order, specific angle order. So let's pick X, let's get my pointer. Let's pick X, Y, 90, X, Y, 90, X, Y, 90. So we're going in the same direction for all of them, and we name them correctly. So we've got triangle A, C, D, if we went X, Y, 90, is similar to triangle C, B, D, which is similar to triangle A, B, C. Okay, we made sure to go in the same direction, all 3 triangles. That is how you know you have the right ones listed. Okay, so now let's look at the relationships between the side lengths of these triangles. And if for nothing else, just to get off this messy screen. Okay, so looking at these, actually let's go right to this board. Okay, so this is the board I want to talk about. One thing I want to add here, this little thing got cut off down here, this guy is C. All right, so let's look at our hypotenuse, and I want to compare the small triangle to the large triangle. So small to large is all we're looking at. So let's say the hypotenuse of the large, that's very easy to see, hypotenuse of the large is AB. What's the hypotenuse of the small? That's AC. Okay, in case you can't see that, remember big triangle, here's my hypotenuse across from 90, small triangle, hypotenuse across from 90. Okay, so we have hypotenuse to hypotenuse. Now, the funny thing about AC, it is the hypotenuse of the smaller triangle, but it's also the leg of the large triangle. So let's look at that. That hypotenuse becomes the leg of the large triangle, so let's put that to the leg of the small triangle. Okay, and that's how we get that relationship. We get that relationship by saying AB, hypotenuse large, to hypotenuse small, is equal to that same hypotenuse that became leg of large to leg of small. Okay, now this gives us a really cool relationship when we cross multiply. Okay, you may remember geometric means. If you don't remember geometric means, don't worry. We're going to see what you get when you cross multiply. Okay, so let's cross multiply this, and we see that AC, if we square that, it is equal to the product of AB times AD. That makes it real easy when you're finding lengths with missing lengths in these problems. Okay, so let's look at that. So if we have AC squared, so the hypotenuse of the small triangle squared is equal to the leg of the small times the hypotenuse of the large. Okay, we're going to see a very similar relationship when we look over comparing the large and the medium. So let's compare the large and the medium. Okay, comparing the medium to the large triangle. Okay, medium to the large. Let's start again with the hypotenuse of the large is AB. What's the hypotenuse of the medium? It is CB. The hypotenuse of the medium also becomes a leg of the larger triangle. Same relationship. So that leg of the larger goes to the leg of the medium. That is how we get that relationship. We say hypotenuse of the large is AB. Hypotenuse of the medium is CB. CB becomes the leg of the large to the leg of the medium, DB. Once again, when we cross multiply, we get a special relationship. We get this geometric mean. Don't worry if you don't know what that is. It simply means if we take the hypotenuse of the medium and square it, so the hypotenuse of the medium triangle and square it, it is equal to the product of AB times DB. So once again, it is equal to the product of the entire hypotenuse of the large and just the leg of its medium triangle. Okay, so that relationship will keep coming back, make things really easy to solve. Okay, last relationship, I promise. And it's the easiest one to see. When we compare the small and the medium. Okay, this is going to be really easy. We're only looking at legs. So this leg here, small leg AD to large leg CD. That large leg becomes the small leg of the medium triangle. So small leg to large leg. Okay, so AD, small leg, to CD, large leg. That large leg CD becomes the small leg of the medium to DB. Guess what? When we cross multiply, we're going to get a geometric mean again. Okay, this time, anytime you have something, remember, we had this small to large, but the large became the small. We had hypotenuse to hypotenuse, but the hypotenuse became a leg. Anytime that thing serves as 2, it becomes something for the other triangle. That's our geometric mean. So we're going to say CD squared. Okay, so CD squared, the altitude squared. Remember, CD is really, really unique in this relationship. The altitude squared is equal to what? It's equal to the product of AD times DB. So this time, when we square the altitude, we get the product of the 2 parts of the entire hypotenuse. Okay, so those are really going to help us solve this actual problem. Remember we had a problem when we started this video? Let's go back up to it. Okay, so first slide, we had a problem. There it is. Let's erase all this other garbage here. And let's solve it now that we have relationships. Okay, so we know that this is 12, and we know this is 5, and we know the altitude is our x. Okay, well we just learned that the altitude squared, okay, if we look at this guy, we just learned, I thought we just learned it, okay, we just learned when we looked at these relationships that if we squared this altitude, CD squared was equal to the pieces of the hypotenuse of the big one. So AD times DB. Okay, so let's use that. Let's solve this with that. We know that x squared is equal to 12 times 5. Now let's say you didn't really get that relationship. Let's say you just used similar triangles and set up proportions. Okay, that's all right too. Remember we had small to large, small to large. So if you only did this by setting up your proportions, you would say take the small triangle, small leg 5 is to the large leg x. Now look at the medium triangle. The small leg x is to the large leg 12. And when you cross multiply these, you will still end up with x squared equals 12 times 5. Okay, so by now you might know the answer to this, but let's just do it on this one page. Let's get a clean page. And let's say x squared equals 12 times 5. So we all know that that's 60, so let's erase it and just put 60. What's the opposite of squaring? Square rooting. So take the square root of both sides. X equals, let's see, square root of 60 is really the square root of 4 times the square root of 15. Square root of 4 is 2, so this is 2 times the square root of 15, or we like to say 2 rad 15. So our altitude has a length of 2 times the square root of 15, or 2 rad 15. Okay, so I hope that helped. Okay, final answer here, okay, equals 2 rad 15. If you have any questions or anything was fuzzy in there, I know my handwriting was a little sketchy. Apparently my handwriting is already on summer vacation. Please put questions or comments in the comment section. And remember, I only solved this because a subscriber submitted it. So if you're doing homework and you're struggling and you don't have to be, or you don't want to be, send your problems to me and I'll solve them. Thanks for watching.